What kind of region is that, right? Do I want to treat that as a type 1 or a type 2? You could do either, but one of them's easier. Look, let's look at type 1. If I do type 1, then if I move from left to right, does the top and bottom curves always stay the same? Yes. If I do type 2, do they always stay the same? Here, this one is the one on the right. The one on the left will always be this line, right? But see, once I get up to here, it switches to a different curve, doesn't it? So I could do type 2, but I'd have to split it into two integrals, and I don't want to do that, so I'm going to keep it as a type 1. Yeah? So I'm going to go with type 1 on this. Type 1. I didn't do this before, but I'm going to go ahead and put my restrictions that I know. I know x is restricted between 0 and 1. Now, I didn't do this before. I'm just showing you a different sort of approach, different notation. All right? Now, what's your restriction on y? It has to be a function. This is a type 1 region. So you cannot just say between 0 and 1, because as you move this left and right, your y value is not free to go as high as you want. Well, you can't go all the way up to 1 here, can it? It's got to stay underneath that one. So we actually need to come up with those two curves. What are those two curves? So do you know what this curve is right here? And do you know what this one is? The bottom one came from this, didn't it? And you could check it, 0, 0 lives there, right? And then if I plug in 1 for x, well, hold on. Wait a minute.
Yeah, that's right. Oh, yeah.
Yeah, x is 1. Sorry, yeah, you get... All right, I had a little panic attack there. So the bottom one comes from this equation, x equals 2y. We agree? The top one comes from what? I mean, isn't that where that plane comes in and hits the ground? Let me see if I can rotate this around. Okay. There's that picture, right? Where that plane came in and hit the ground right here. Isn't that what we're talking about? And that means it comes from the equation of the plane when z was 0. So what's the equation of the plane when z is 0? It's x plus 2y equals 2. Now this is a type 1 region. So I want to solve both of those equations for y. So this should be y is equal to -1/2 x plus 1. Solve that for y. Solve this for y. Y is equal to 1/2 x. And in terms of matching up with the formulas we're using, this one would be g sub 2 of x. This one would be g sub 1 of x. Wouldn't it? Okay, so now writing it this way, what's the lower limit of g, or y, sorry? 1/2 x, and the upper would be -1/2 x plus 1. There you go. That should be everything we need to set up the double integral. See, you can tell these kind of get a little messy with the, just the visualization of things. So double integral, 0 to 1, 1/2 x to -1/2 x plus 1. What are we integrating? z equals 2, so 2 minus x minus 2y. That was that surface right there. And then d y dx. There we go. Dot, dot, dot. So when the final comes around and I ask you a problem like this, it will be set up the double integral. Do not evaluate. Okay? So you'll just set it up. I mean, there will be a problem. There will be at least one problem on the final where you have to evaluate the whole thing. But setting up, getting to this point is where I'll want you to get. So we can, you know, not waste time doing integration. All right. That was interesting. Example 5. Order might matter. This looks harmless enough. I love this problem. This is outstanding. So you look at that and you're like, all right, sure. You know, trying to find the volume below this surface over some region, and I just have to be able to compute that, right? And then you go, wait a minute, what's the antiderivative of sine y squared? So you go to Wolfram alpha, and you type in integrate sine y squared. And it returns to you the square root of pi over 2 times capital S of square root of 2 over pi times y plus a constant, where capital S is, by the way, the Frenzel S integral. That should look like complete nonsense to you, all right? Which it is. Basically, Mathematica, Wolfram alpha is saying, you're not doing that by hand. That's the long, ugly way of saying there's no way you're doing that by hand, all right? Take more math classes, you'll figure out this is just kind of like an error function. It's a way of measuring error. So you just go dot, dot, dot. That's it. Move on to the next problem. I can't integrate sine of y squared with respect to y because it's something I've never been able to do. Oh, by the way, you could do it with a power series. You could get an approximation. But I wonder, hold on. I bet you Wolfram alpha did it somewhere. There it is. So the program, where's the, oh, I moved it right to the place you can't see it. Here's your series expansion right here. Here's your power series expansion. So if you use power series, you can get the approximation as close as you want. And that's how they're able to get a numerical answer. So we can't, we're not going to say there's no way we can do it. We can, but it'll be an approximation. What would be better? If, right? The big if this was dx dy, now that would be easier for me to integrate, because if I was integrating with respect to x, that would all be a constant, and then the antiderivative would just be that times x, wouldn't it? I wonder if I can switch it. If these were both numbers, I could, right? If these were numbers and these were numbers, I could switch it. But they're not.
Isn't that x equals sine y squared, and then you can solve for y?
Wait, hold on. Say again. Isn't what?
Like the integrand, or what's in there?
Here?
Isn't that x equals sine y squared, and then you could solve for x? I mean,
No,
sorry,
that's
solve for
that's
y.
z
Oh,
equals.
it's z.
Yeah, it's z equals that.
Okay.
So watch, check this out. Watch what we're about to do. This is what we know. Right? That's what the double integral tells us. Right? Those are restrictions on x and those are restrictions on y. I'm going to go backwards now and draw the region from that information. Okay? I know that my x's have to be between 0 and 1, don't they? But my y values are between, what? 1 is the top and x is the bottom. So 1 being the top is this, right? X being the bottom is this. Yes or no? Y equals x, 1. And the way this integral is trying to approach the problem is by treating this region like a what? Type. They're trying to treat it like a type 1, right? I can switch the order of integration if I change it to a type 2. The question is, can you convert this to a type 2? Yes. Because if I draw my double arrow this way instead, will I still maintain the same left bound the whole time and the same right bound the whole time? Yes? That's what I'm going to do. I'm going to take the original problem. I'm going to give up on the fact that I'm never going to be able to integrate that. I'm going to go and look at the region and say, I'm going to switch it to a type 2, and then when I go back and look at this, it'll now be dx dy, if I can make the switch. So all I'm going to have to do to make the switch is, instead of looking at top and bottom, look at left and right. So this left bound, which we said was h sub 1 of y, what is that left bound on the y value? Or sorry, on the x value? 0, right? That's fixing my x at 0. It's always 0 the whole time. This one right here, h sub 2 of y, is this equation, which, what was the equation that drew this? Y is x. It's that equation solved for x instead of y, but it's already solved for x. So this is just y. Y? And then I just need to know my restriction on my y values. It goes from 0 to 1. So I can draw the same exact region, get the same exact answer, if instead of this, I go y is between 0 and 1, and x is between what this time? 0 and this side, y. Do y'all see that? That's pretty clever, right? Switch this over, double integral, 0 to 1, 0 to 1, 0 to y, and then the same integrand, switched